This will hangover en constateren.
This will be a blast indeed. Yes, let me start by thanking the organizers in particular for.
Can you turn the microphone on?
Oh, the microphone on.
Hold down the top button.
Is it working now?
Hold down the top button.
Hold it down.
Like flickering.
Yeah. Good. So I want to talk about some adventures that I'm undertaking with condensed matter physicist from Utrecht, Henk Stoof, and Vivian Jacobs is a PhD student who's kind of working on the interplay between condensed matter and ADS-C related stuff, and some earlier work that we did with Umut Gursoy and Erik Plosjen, together with these people also. And the topic is going to be about Weyl semimetals. This is a little bit of a new topic in condensed matter as well, like 2 years old basically. Of course, it goes back to the days of Weyl himself, so depending on how sensitive you are to history, you can go back all the way to 100 years. I want to keep this presentation quite sort of simple, focusing a little bit on the concepts. And then later on, I'm going to talk about some results and the implementation of holography to describe these Weyl semimetals. In particular, I will focus on conductivities. Now, let me first tell you what are Weyl semimetals. So, semimetals in condensed matter, we like to classify materials also according to their band structures, conductors, metals, semimetals, insulators. And semimetals are just like on the borderline between insulators and metals in the sense that conductance bands and valence bands touch each other. When you translate that in terms of dispersion relations of particles, fermions, then the dispersion relations are in the omega k plane. They are just gapless. And if you have linear dispersions, for instance, the simplest setup is that the conductance bands and the valence bands actually touch in one point, and that is the main characteristic of a semimetal. So an example of such a system is graphene, and that's in 2+1 dimensions. Where the system basically can be described by 3 Dirac fermions in 2 dimensions, and that is, of course, well known. And what I want to do is now take a 3-dimensional version, 3 spatial dimensions, and characterize the semimetals as systems like this here, where the dispersion relations are linear, but gapless, and but now based on a chiral spinor. So in 3 dimensions, the Dirac fermion of 2 dimensions actually becomes, because it has 2 components in 2+1 dimensions, if you lift the 2 component into 3+1 components in 3+1 dimensions, it becomes a chiral spinor. I will explain a little bit better. And so Weyl spinors are kind of nice. In condensed matter language, the simplest Hamiltonian that describes a Weyl spinor is something like just a free Weyl spinor. It has some, let's say, Fermi velocity and then sigma dot k. And this kind of Hamiltonian generates these dispersion relations where you have the 2 components of sigma 3 just, well, I put k in the 3 direction, gives the linear dispersion relations. One can make it more complicated and have anisotropic Weyl semimetals. Then you have here matrix Vij and then sigma times k. But I will focus on the simplest setup. Now, these are kind of interesting for the following reasons. When you have a Weyl spinor or a Weyl fermion, chiral fermion, it's the same word for the it's a different word for the same thing, then they are projected. You cannot. They are protected against mass gaps. This is because when you have a chiral fermion, you cannot write down mass terms for it. And let me illustrate this in a more quantum field theory language. If you have in quantum field theory a Dirac spinor, that's a 4-component spinor psi, you can go to a basis in which it's called a Weyl basis, in which you can write this as two component spinors, lambda and chi, and they're both the chiral projections. So lambda is essentially equals 1 plus gamma 5 psi, and chi 1/2 1 minus gamma 5. Maybe I should write gamma bar psi in a basis in which gamma 5 is just 1 0 0 minus 1. And if you write down the Dirac Lagrangian for a massive Dirac, then it is simply, so these are the very simple things that I first want to explain. Then it is, if you project it in this basis, it becomes something like this, kinetic term for the two Weyl components, and then you get a mass term which looks something like. And here the gamma matrices are using the Pauli matrices decomposed like this. Sigma mu consists of unit matrix and the Pauli matrices. Sigma bar is minus unit matrix and the Pauli matrices. And you see that if you have a chiral spinor, you set just chi equals to 0. You only have lambda, that's my Weyl spinor. If you set chi to 0, you see that the mass term drops out, and it's actually not possible to write down a mass term for the chiral spinor or the Weyl spinor lambda by itself. You can write down Majorana masses. Majorana mass would, or Majorana particle would be when chi is equal to lambda. Then you get mass terms of the form lambda lambda, and then M is called Majorana mass. But it is not an interaction, or it's not a mass term quadratic in lambda lambda bar. That doesn't exist. That's impossible. So Weyl spinors are called also condensed matter. You hear the word topological because they can never create a gap, and they remain massless. And that is very different mechanism than in 2 dimensions for graphene. Here, the fact that you have a chiral spinor projects or protects the mass to or prevents a mass gap to form. Unless you have interactions with different chiralities and particles, antiparticles can annihilate, that can create a mass gap, but that is not the case actually that we are considering. So,
is it just the relativistic invariance of the Lagrangian that you're writing down that prevents the having a sort of bar lambda? If you gave that up, would you?
I will give certain things up in a moment, but still, if you just have 2 component spinors, the spin transformations on the 2 components, you can still not write down, also in the non-relativistic case, a mass term for a chiral spinor. Yeah, here it's kind of explained in a relativistic way, but I actually don't need that. Good. So if you think in terms of these Dirac fermions, you actually get 2 copies of Weyl fermions, and so that means that you have 2 Weyl cones for each of the chiralities. Let's say the plus and the minus, or the lambda and the chi, if you want. And what actually happens in more realistic materials, or more realistic Weyl semimetals, is that certain interactions are going to be induced that are kind of forbidden in a theory with relativistic invariant and time reversal and parity systems, a parity symmetry, that you can add interactions of the following form. I go back to my in the Dirac basis. It looks something like follows. Okay. So now I take, this would be of a massless Dirac fermion, m is equal to 0. Then one can add terms of the following form, some delta k slash gamma 5 psi. So of course one breaks rotational symmetry. You pick a certain number. I call it delta k mu, which is directed in the spatial directions, times gamma mu times gamma 5. And the effect of that is that the Weyl cones, because of these terms, actually split. But because of the gamma 5, the Weyl cone of one chirality is shifted to the left and the other one is shifted to the right. Something like this.
Can I just come back to this point about the mass? I mean, the chiral, because the chiral fermion is complex, so you have a chorus of the complex conjugate. In the standard model, for example, I mean, we have chirality because you have a representation, because the fermions in a representation that is intrinsically complex, right? So the complex conjugate is a different representation. But I mean, if you just have a single, if you just have a single Weyl spinor, you always have a complex conjugate. It's not in any, you don't have any other representation, let's say.
Absolutely. So the conjugate of lambda is lambda bar, and that.
I mean, if you wrote down some gauge theory, four-dimensional gauge theory in groups with just U1 to something, I mean, that wouldn't be a chiral theory. You need something like SU3. Then the complex conjugate is a 3 bar. You need to put it in. You need to put the fermions into some.
Yeah, this would be the 2. If we do the spinorial or spinor transformation, and this would be the conjugate representation, lambda bar.
What I'm saying is that because it's complex, you always have actually 4 components over the reals.
That's right.
It's always equivalent to a Majorana spin. And you can write down a mass for a Majorana spin.
Yes, you can write down. So that's what I was saying for Majorana. That's the case when chi is equal to lambda. Then you get lambda times lambda. These terms, of course, break chiral symmetry.
Okay,
So I agree, but
would be lambda for
yes. So for Dirac, so for Majorana, this is for Majorana spinor. Of course, this talk is not about Majorana spinors, but anyway. Chi is equal to lambda, and then psi is equal to lambda bar, and that's a Majorana spinor in this Weyl basis. These are the chiral projections of a Majorana spinor, and then the mass term still can exist. Yeah.
Another question, Stefan. What do you mean with delta slash? I mean, I recognize.
So delta slash is basically delta k mu gamma mu. So there's a 4x4 matrix,
Okay.
and this is something that experiment tells you how this splitting is done.
It just shifts things in the.
It just shifts, and then the gamma 5, because gamma 5 is 1 minus 1. The 2 chiralities are shifted into different directions.
Right, so this will typically happen because of spinor coupling, I guess.
Yes, so I should say this is important, although I don't know very much about it. Most of the work in the condensed matter literature is done purely at a theoretical level, but last week there appeared the first paper where there is an experimental realization of these Weyl semimetals, and so it looks to me like this is a promising new field, although it remains to be seen. Actually, these systems are not so clean as graphene, for instance, and
These kind of things used Abrikosa a long time ago and explained some experimental data of these pentagonites.
this is why I'm saying, depending on how sensitive you are to history, this goes back to 200 years ago or to 50 years ago.
Various minimal experiments, close connection already existed. This kind of model flow.
You will have to explain me afterwards. Then.
This is topological, I don't think.
So the chemical compounds, that these people, so these are groups in Oxford, Stanford. The chemical compounds is based on natrium and bismuth, and they apparently do these things.
Ian Fisher, I guess. Ian Fisher and stuff.
I can give you the names. And the theoretical work, actually, I should say, the theoretical work is well, there's many people associated to it, but one of the people who worked on this first is people like R.E. Turner and his collaborators, and Leon Balens from Santa Barbara, and Viswanath, but yeah, I don't know him in person. So good. So the separation. So here's the positive chirality, let's say, and here's the negative chirality. So you split these cones, and especially high energy physicists, they know very well that when you have chiral fermions, there's chiral anomalies, and that means that chirality, let's say currents or chirality, is not conserved. And in these condensed matter setups, that is kind of like realized that you can have transitions from one cone, from one chirality cone to the other cone. And so there's all kinds of interesting consequences also for transport phenomena because of the chiral anomaly. One other thing that is very interesting, but I just mentioned it, but I'm not going to talk about it, is that you can think of these Weyl cone also as magnetic monopoles in the following sense. If you solve the Hamiltonian and the wave function, then you can actually construct from these wave functions a kind of Berry connection that basically goes something like follows. So you have the wave functions, let's say in momentum space. You compute the inner product, something like this, and then you can compute the curvature of it, and you integrate it, and then actually the result of this is that you get plus or minus 1 depending on what the chirality of these two objects are. So this is, what is it called, the Berry connection or Chern connection. Yeah. Also, when you separate these cones, there's other interesting phenomena. If you consider this Weyl semi-metal with boundaries, then you can have edge states, and these edge states, there's lots of interesting things to say about it, and you can have, as a consequence of that, Fermi arcs connecting cones, etc. But I won't focus on this today.
Yeah, I guess there's this general theory that, right, much of the structure is poured from the topological insulator, so
yes,
the gap is protecting everything.
Yes, yeah.
Here because mass is there much more.
That's right. Here is because of the chirality. Yeah.
To shift.
Yes. So you get also anomalous Hall effect and lots of these phenomena that we know also from other areas do come back and find their place here. So lots of things that I find quite interesting about them. And what I'm going to focus on is the conductivities, and in particular the optical, or well, conductivity, just the electrical conductivity basically. I'm also looking at the diagonal part, so I'm not going to do the Hall effect. And this conductivity can be computed for the case of a free system. Basically, you apply an external electromagnetic field, and this is a nice quantum field theory calculation. So compute. There's various ways to compute the conductivity, but basically it kind of boils down to this Feynman diagram. So this is an external magnetic electric field. You let a fermion or the Weyl fermion propagate in the loop. And this gives you the polarization tensor. From the polarization tensor, you use Kubel's theory, and you can actually compute the conductivity from that. And so this gives sigma as a function of temperature and omega. And for t equals 0, this is an exact result in the literature. It can be computed, and what you get is that sigma of omega is equal to e squared over, I put all the constants, times omega. So that
Divergent. 3 plus 1 dimension.
yes, very good.
I mean, some small scaling problem.
So you can regulate it. Actually, you can look up Peskin and Schroeder and do the whole dimensional regularization. And I thought this is how also we did it, although the condensed matter.
Condensed matter physics is kind of pathetic because
Yes.
the calculator is just these atoms, what was it, bismuth or sodium.
So it's basically
Yeah.
on a lattice with a lattice scale.
Well, there's various ways of answering this question. If you, for the conductivity, that is actually finite because if you compute the polarization tensor for this diagram, then to compute the conductivity, you have to take the imaginary part, and the imaginary part of it is fine. So you can for this purpose, you can throw away the divergence, and it's irrelevant.
Right, so from condensed matter physics, you learn that your free regulators basically living in a theoretical world that there's no bearing to reality because UV is always boring in our case. Yeah, it saves you in our energy physics.
Right.
Don't worry about UV.
Yeah, that's right. Yeah. So of course, this C here is actually this. Yeah, it can be the velocity over there, depending on the system that you have. So these Weyl cones don't have to be like light cone, like they can have just a finite opening, depending on what is the velocity.
So it's not at all like twice graphene, right?
No, so graphene has just a constant conductivity, and this has just a linear conductivity for omega.
And it's depending whether you split the cones there or when you...
No, that's important. So from now on in the talk, I am going to, well, this result actually is independent whether the cones are split. The splitting of the cone comes in the whole conductivity. That's proportional to the splitting. But the electric or optical conductivity, actually, it doesn't matter if they are splitted, but they are proportional to the number of cones. So if you have, for instance, two cones on top of each other, you just multiply by the number of cones. They each contribute in the
It's
same.
basically because 3D, right? I guess.
Because?
It's a 3D, three
Yes,
dimensions.
yes,
That's why you take the two
Different
space dimensions,
states,
constantly,
Right.
you get this.
Yeah.
Also, it's n times graphene in essence is 3D.
Yeah, in a way, except that you get now linear. Yeah, it's a little bit dimensional analysis. That's right. So people in the condensed matter literature have also tried to include interactions because this is, I want to develop the story now at interactions and then do the strongly coupled version and go into holography. Now interactions are a little bit similar, a little bit different than graphene. What we get, of course, we have Coulomb interactions, and so essentially what happens, at least in the calculations that I've seen in condensed matter, is you get a renormalization of the charge, and also due to the Coulomb interactions, then the omega becomes omega log omega. So if I add Coulomb interactions, then sigma, so then essentially E goes to some kind of renormalized E, and we get logarithmic terms in the conductivity omega log omega. So that is one result that is in the CondMat literature, and one.
I guess the direction is irrelevant.
Excuse me.
They are irrelevant or marginally irrelevant, whatever. If marginally irrelevant, that is log.
Yes. Yeah. Good. So one can add impurities. Now things become complicated there, but I'm not going to add impurities anyway. There are some results on finite temperature, but it looks a little bit complicated to me. So you see where I want to go to now. I want to consider strongly coupled versions. There's a little bit double-sided, just like for graphene. In some sense, they are free fermions. On the other hand, there are Coulomb interactions, and the Coulomb interactions become strong. So, so we decided that we want to study, let's say, strongly coupled Weyl semimetals. Because
it's similar as in graphene that because the Fermi velocity is much smaller than the light velocity.
yes,
The fine structure constant actually
is large.
quite large.
Yeah, and that's the same here. Of course, V depends on what actually is the crystal structure, the lattice structure, the materials that are
It's
used.
set by the electron mass and therefore the velocity.
That's
It's
it.
tiny compared to the
Yeah.
light velocity.
Yeah.
Is there any parameter which related to interaction, like a res parameter is typically the strength of interaction?
I don't know what a res
Just
parameter.
ratio of this interaction in comparison to kinetic energy, for example.
Maybe there is. I don't know. I mean,
It's effectively zero density, right? So it's really the fine structure constant that matters. That's all the coupling constant.
So
Just think it's simple because it depends on
It's
density
zero
of
density
electrons.
effectively.
It depends on density of electrons.
yeah, I'm going to look actually. Yeah, so that's important.
So adding to this to say this is, you have done all that work and you have used these electrons. In principle there are pair group interactions when you go to the UV of this, right?
Yes.
And then you're effectively at zero density. And these
That's
things are checked in graphene. RS is not relevant.
RS is called, yeah,
Just fix this, huh?
People check in graphene RS about what?
Mass interrupt kernels at zero density. Don't know about RS. No, understood.
So now I want to make an argument why holography is actually perfectly suitable for studying these systems. And the argument goes basically as follows. It basically is in the papers of the MIT and Leiden people, except that they did holography from 4 bulk to 3 boundary, and we're going to have 5 bulk dimensions and 4 boundary. So you start here with a 5D bulk, and you take a Dirac spinner, and a 5D Dirac spinner has equal number of components as a 4D Dirac spinner. It's when you go from odd to even, or from even to odd, that you get the doubling or not. Now, when you go through the MIT Leiden papers on how fermions are projected to the bulk, then basically what you do is you decompose this by using the gamma matrix in the radial direction. So let me give a pictorial view. This is let's say ADS in planar coordinates. Here could be the black hole. Here's the boundary. There's the radial direction, and then there's the Clifford algebra, the gamma matrices. M psi plus minus is equal to 1/2 gamma r times psi. And depending whether you're on even or odd dimensions, you choose something different from gamma r, and this is all worked out in these papers, so I'm not saying anything new here, except the following observation. So for odd dimensions, so if we call this d plus 1 and this d, okay, then d is d plus 1, then so for odd d, so odd boundaries, we take gamma r, or gamma r can be chosen to be 1 minus 1. So this is basically the chirality operator now in the bulk. And if you're a chirality operator in the bulk, then these are the chiral components. But on the boundary, this becomes then a Dirac fermion. This is the source, and this is going to be basically the response. So your boundary theory is a theory for a Dirac spinner. And that's what is being used a lot in ADS4 CMT3. However, for even D, which is the case I'm interested in, what you choose is the chirality operator in even dimensions. So gamma 5 in D equals 4. That means that the 5-dimensional Dirac spinner spits out, it's the same logic again, one you treat as a source and the other is determined by the Dirac operator, but now the source is a chiral fermion. So that's exactly what I want, because we're dealing with wild spinners on the boundary, so I want the holography to give these chiral spinners, they are just naturally spit out. And that's very nice. It's a trivial observation. All the equations have been in these papers, and so we're going to use that. And so the Dirac equation, let me set up some notation. So basically, we treat psi plus as a source, and then psi minus is solved by the Dirac equation. And well, in our notation, there is some matrix, some operator xi. You go to momentum space. It's the usual story. And then this xi, using the MIT Leiden story, is just gives you the Green's function. However, we're going to do something differently, and one can debate about it, and it's actually not without debate. We do holography a little bit different in the following sense. If you go through the normal holography material, then what you compute, if you do this thing, you get correlation functions for composite operators. I don't want correlation functions for composite operators. I basically want correlation functions for my fermions. So I have to figure out a way how to get correlation functions for from holography for basically elementary fermions. And we have a method that does this. It's actually not completely new either, but in this context I haven't seen it before. So what we're going to do is we're going to, on the boundary, actually, this is my source. I'm going to make my source dynamical. So, well, usually we introduce some kind of cutoff slice here at R0. And then you can call it a UV brane. And then at the end of calculation, send R0 to infinity. So what I'm going to do is consider bulk actions or total actions, which are your favorite gravitational system. It can be Einstein, Maxwell for black holes. Then I have my bulk fermion, my Dirac fermion, d5x square root minus g psi bar d slash minus m psi. And now I add boundary terms at this slice located at r equals r0. So d4x, there's an induced metric, h. And then I add the following term. What you usually see in the literature is just a kind of like a term which is quadratic. So you've quadratic in the fermion fields, psi plus, dagger, psi minus. And, okay, I don't know how much detail I should present, but so what I'm going to do new is I'm going to add a term dagger d slash psi plus. So the usual story, the MIT Leiden story, is you add this bulk here with this boundary term, and what we add to is on this slice at R0, we're going to make the source dynamical. So that provides some kinetic energy for psi plus, and I introduce a coupling Z. When Z is equal to 0, you're back to the known story. When GF is equal to 0, essentially this source essentially decouples from well, the bulk system, and you get just a free fermion. So
Another way of saying semi-holography, the positive plot.
well, the end result looks very similar, but we're kind of, well, I have some things with semi-holography. I think this is better. I want to call it not semi-holography, but holography 1.5. Or, but now you see.
To ask is whether there's any observable difference between semi-holography and this when you go to the deeper.
I have to go through the details. There's some differences, but I don't know how substantial it is. So you can say that this is a bulk derivation of semi-holography. So what we do is we plug in the Dirac equation, the solution of Dirac equation, but you get 0 from here, so because this is first order. So when you plug in this relation into here, you eliminate psi minus, and what you get is an effective theory for the source, psi plus, which looks like something like minus d4p, 2 pi to the 4th, psi plus dagger, square root minus h. I rescale also the psi's with a factor of z, d slash. I go to a Fourier transform, and we get something like this. Psi at R0, p, and psi plus. So this thing here is going to be my Green's function. The Green's function for my dynamical source, which I treat as a elementary fermion, basically. Or this is the inverse Green's function. Yeah. Now I have to do some double scaling limit, and this is what I don't see in the semi-holography paper. So what I'm going to do now, because in the that's why I wrote these powers here, there's all kinds of powers of R0. If you take R0 to infinity, you get some things that blow up, and you have to take a limit carefully. So the double scaling limit is to send R0 going to infinity, GF, the coupling here, going to 0, but in such a way, Z I also keep fixed, in such a way that this ratio here, GF R0 to the 2 minus 2m, becomes a little bit technical perhaps, but stay with me for a little while. We take this to be constant. So then this Green's function has a well-defined limit, at least as long as this psi is well-defined, but this in all examples it is. And what?
How can you choose on this psi? Does it come from what?
This comes from, this is where the hard work goes in. This comes from solving the Dirac equation. So the Dirac equation, we have a 5-dimensional Dirac spinor. You have to couple it to gravity, and you have to solve the Dirac equation in the presence of this curved space, which we take a black hole. And yeah, since it's first order, basically psi plus and psi minus are not related, but they are, there's a relation between them, and the Dirac equation will relate psi minus to psi plus, and that operator, or if you go to momentum space,
This is the proper limit, right?
this is what?
You'll have back reaction, so the psi.
Well, yeah, okay, there is the back reaction problem. We treat this fermion as a probe fermion. The back reaction problem is known to be very complicated. There's some progress being made, but at this stage of our investigation, we have not done any back reaction.
Because the psi are just MIT Leiden fermions.
Yes, exactly, yes, yeah.
But now you have these boundary fermions that are talking with these things that
That's right, yeah.
people say, well, that's for some other stuff.
So the language that people like to use, because especially when we want to compare to semi-holography, is that we have a kind of CFT dual, which is basically the dual of this system here, and you have a fermion that couples to the CFT, or at least it couples to a certain operator, the operator for which psi plus would be the source, and then that operator will have a Green's function, which is basically what this psi is.
What about scaling for this psi? Is there some what kind of function is it approximate?
Well, in pretty much almost all cases, you have to solve it numerically. There's a few cases where you can do it exactly, and then you get ratios of Bessel functions, etc. And yeah.
Just MIT Leiden business.
Yeah.
You have that. The specialty is
Exactly. Yeah.
you
Yeah.
have this extra free fermion field that
That's right.
Anja is talking
Yeah. That's
in
so
a
that,
different
yeah.
way than in the
Yeah.
Volkan-Poshinsky way, where you basically extract the free fermion
That's right.
out of the build.
Yes.
Which in principle is
So that's the only difference. But since people have asked me a lot of questions about this, I thought to present it now, kind of like.
I have a question. You have said that the psi minus is regarded as an expectation value. So I'm confused that because psi minus is a fermion field, it's a non-homogeneous. So why it can have some expectation value?
Maybe that's inappropriate language. The only thing what I mean is that, as usual, when you have a Dirac spinor, you split it, and half of the components is determined in terms of the other half by the Dirac equation. That's the only thing that matters here. Yeah.
This extra counter term that is proportional to Z.
Yeah.
Do you need that also to have a well-defined variation principle? Is it really different from the other companies?
Yes. So very good. So basically, how this term is determined is by having a well-defined variational principle, and so what we do is we impose kind of like Dirichlet boundary or variations of psi plus. So and we can vary psi minus arbitrary on this slice. So that means that if you don't vary psi plus on the slice, then well, this is also a well-known story. You can add here any extra term here which only involves psi plus, and that's consistent with the variational principle. So you can have here any other interaction if you want, based on only psi plus.
But it's like a finite counter term. Or does it do anything to the? It doesn't remove any divergences.
This doesn't remove any divergences, right? Yeah.
Anyway, you can link this to top-down. Is there in top-down imaginable and this type of system?
I think so, but we haven't done this. But the obvious thing
To see, and then you're just external field to it as top.
The obvious thing to do, if you know, in string theory you have a stack of D3 branes, you take one out, but you have to be very careful, because if you just simply take out one D3 brane, you push it to infinity, you just get a free fermion, it decouples from the entire thing. And because we take this double scaling limit, it does not decouple from the CFT. But I don't know how that really comes from a top-down construction. It would be nice to do this for D3 branes, and then we would have a string theory description. Now you can kind of see what is the outcome of this. The outcome of this is that we get a new Green's function, which looks as follows. So the retarded Green's function is now in momentum space. Well, the signs don't really matter. Omega minus sigma dot k minus something as follows, where sigma of p is given by minus g limit of r0 going to infinity, r0 to, this is just plugging in stuff. And p mu is just minus omega k. So we get a Green's function for this source, for this fermion, which has, well, the canonical form for a fermion with a free propagator and the self-energy. And the self-energy is basically what used to be the Green's function of the MIT Leiden system. Actually, it's the inverse of that. That's a little subtlety that has to do with alternative quantization, because we're integrating over the source, but that doesn't matter. So what used to be the Green's function is now the self-energy, and if you use the picture of a fermion interacting with the CFT, you're kind of integrating out the CFT degrees of freedom, and that produces a self-energy that contributes to the fermion propagator. And so now the framework is all clear, I think. Now we can start to apply it. So if you were asking for some exact results, there are for temperature equals to 0, we have exact formulas, which we have for arbitrary k and omega. But if I also take k to 0, then sigma looks some number which is related to this g, but some coefficients, omega to the power 2m, and m is the Dirac mass. And I should say that this stuff here, you know, there's the Brighton-Lohner-Friedman bound, and there's this window above which you have to change quantization scheme. So this holds for all values between -1/2 and 1/2. You can also do m equals 1/2, and then you basically get, this is a point where you get, if you solve the Dirac equation, you get logarithmic terms. We can deal with that. If you do that, you work it through, you get essentially some number times omega log omega for m equals 1/2. In fact, in the paper, we also did Lifshitz case. You can do that, and then these 1/2 becomes 1 divided, well, or m over z becomes, well, we get arbitrary dependence on the dynamical exponent.
So it's pretty much the same thing as in a normal MIT Leiden thermal scheme, to use a deep infrared, you still want to have a propagator.
Yes, yes.
And you somehow lost these, let's call them the domainal fermions, that's sort of the Brighton group in front of the horizon producing the dispersions in the normal case. So it is again this.
The dispersions will follow from, well, you compute the spectral density.
Right, so it's not propagated. Right, when you are in this regime where you just see the MIT light and fermion, light and MIT fermion business, you start to see these fermion surfaces. Right, because you bind fermions at the domain wall, right? And you fall in from a deep UV, and you first get sort of trapped at these bound states of the radial direction, and then you tunnel through, and you find out your deep infrared in this propagator.
Right. That is all not yet incorporated here. This is at zero chemical potential. We're doing basically just an ADS, or you can do Schwarzschild ADS if you want to have temperature. There's no chemical potential yet,
good.
and all the interesting stuff that comes with it. So I cannot go near horizon, for instance, and have ADS too. That is not yet in here.
There we are.
But we can do that, but that's just a matter of carrying out the program. So I want to go back now. Now the machinery is there. So now I can go back to the problem of conductivity. And since we now have a Green's function, we can look again at this diagram. And instead of using the bare free propagator here, we're going to use the Green's function, including the interactions.
Can you say again what kind of operators are sourced by this boundary theory?
Well, we don't know what these operators. That's the usual story. You don't know exactly what you know the dimension of the operator.
But you said that you motivated it in the beginning by saying that you don't want large ones, but you just want single particles.
Yes. Well, what you know is that the operators typically don't have dimensions of a elementary fermion. They should be thought of as composite operators.
Yeah, so that's still true, of course.
For instance, one of the things, well, we made a little bit of a point of that, but I don't think it is that important. So since we have here elementary fermions here, and our idea is also in the long term that we should be able to maybe make contact to ARPES experiments. ARPES experiments really measures correlation functions of single fermions, and so that's why we kind of wanted to push in that direction as well. So the Green's function constructed in this way satisfy Kramers-Kronig relations. All poles are in the lower half plane. It also satisfies the sum rules for elementary fermions. You can check that in all these things. But of course, it is true that I think the most interesting regime is the infrared regime, where the interactions become well known. You see, so become important. For m smaller than 1/2, this is a power law that goes slower than omega. So in the far ultraviolet, it is actually you get back a free theory.
Because it's more very similar to these Polycastro and friends. Right? Have now done this job very carefully for the 2 plus 1 dimensional case, the usual MIT lighting case, but again assuming the computer conductivity, just plugging in the renormalized fermion propagators.
Yeah. Oh, I should look at, yeah.
You
So
get different stuff. I mean,
we get different stuff, but the philosophy is the same. But we're not yet completely done. So now I go into the territory of unpublished work, but we hope that we're done soon. So if we go back to this Feynman diagram here to compute the conductivity, what you can now do is use the Green's function, including the self-energy. But that's actually not good enough, because if you do that, well, maybe I'll do that on a different blackboard. Because there's vertex corrections and there's self-energy. And to get the vertex, the self-energy, I told you how to compute it from holography. But the dressed vertex is kind of hard to get that out of holography. Now you need the dressed vertex also if you compute polarization tensors to satisfy transversality conditions. And if you only take the dressed Green's function, it does not satisfy this. Now one can tell stories about this. That's where Henk Stoof is. He has some experience with this. In all the examples that he knows, the contributions from the dressed vertex are comparable maybe to the contributions when you include the dressed Green's function. It's just a change in numerical coefficients. Now, that's a statement, could be true or false, but let me say what we did. What we did is
Because when you are in the
it's a little bit,
Henk knows what to do, but when you have a really strongly rejecting
Yes.
conductive fixed point, you have to know what to do.
yeah,
Right, and Faulkner or Wosinski would say these things are 1 over n suppressed, but be aware of the word identity.
yes, but and it's exactly the word identity
Word
that,
identity, yeah.
well, we are still working on this, but for the moment I can only give you the result when you take the dress screens function without the corrections to the vertex. And I hope we can still kind of like make progress. You could maybe determine part of the vertex corrections from imposing the word identity, but we're not yet done with this. So this it's clear you can carry out this program if you just use the self energy, and then you turn the crank and you make plots. And I'm going to show you these plots. Can I get the screen down, please, now? Works. Okay, so look at the plot at the left. So these are basically the Weyl cones that I talked about earlier. And what we plot here is the spectral density. Spectral density is basically the imaginary part of the retarded Green's function. It just tells you where basically the particles.
Wording is absolute convention from this matter to call that A and not rho.
That's true, yes.
Yeah.
I know these conventions as well. Okay, good. Yeah, it doesn't matter. So what you see here is that instead of getting sharp cones, so in the case of a free fermion, this would be basically the Weyl cones, and or the Weyl cone, which in the free case would have like really poles at the locations where omega is equal to k, if you work that out component per component. And what happens now because of the interaction is that cone is kind of gets a little bit fuzzy, gets a bit smeared out. But only in the inside part of the cone. So you see here that this is not a steep delta function. It just slowly goes up, and you get a peak located at omega equals k3 in this case. On the other side of the cone, so outside of the light cone, there's no spectral weight. I think that's all kind of standard. So we reproduce. Yes, yeah.
Completely noise invariant construction. This has to be.
And it has to be, and it does work out. Well, actually, for finite temperature, that changes.
Yeah, it's different. Great noise invariant.
Yeah, exactly. Yeah. So the cones get a little bit like smeared out. This is for quite low temperature, and here's a typical mass, m equals 1/4. And when you raise the temperature, so this is in some dimensionless units, 130. If you raise the temperature, the smearing out of the Weyl cone produces something like this. Here the peak gets smaller and smaller and gets smeared out, and now there is some spectral weight on the other side. And I think this is all a kind of standard. Now, you can use these Green's function spectral densities to compute the conductivity, or numerically, this is numerical work. We do this for finite temperature as well, and we get the following kind of curves. Something like this here. So instead of getting a linear behavior in omega, what we get is the following. So here's various results for various temperatures. Here's the result for t equals 0 is the blue line. So it starts from 0 again. But then due to the interactions, we don't get a straight line. We get a power law. I'll write down what is the exact power in a moment. And then for increasing temperatures, there is a certain offset. So for non-zero temperature, even at 0 frequency, there will now be a conductivity. And another thing that is maybe interesting is that these lines, at some point, they cross other lines with higher temperature. That is because At higher temperature, I just showed you that the Weyl cone actually becomes a bit smeared out, and there's much less spectral weight there, so there's much less particles that can participate in the conductivity. So these curves, they grow much slower than the lower temperature case where the spectral weight where there's more spectral weight.
This is satisfying gross hydrodynamical principle. So when you have a finite density system, then you cannot have finite spectral weight at zero. Excuse me, have only the delta function.
Yes,
Right?
yeah.
In graphene, right, because you have this particle conjugation, you have cone, you lose momentum conservation, so you can have finite weight even at zero temperature. And that you get here finite weight at
Exactly.
temperature is
Yeah.
like the same choice in
Yeah.
graphene. So you don't violate any Gauss principle.
Yes. So I think all our results are kind of like producing the physics that any condensed matter person would sort of already
Well,
guess.
it's simple, right? Because this is really about the word identities and
Yes, okay, that's true.
Violate.
Yes, yeah, we don't seem to violate. So that gives a kind of reassuring feeling that indeed that argument that it's all maybe in in an overall factor or something. I don't know.
you have to work harder, right? At finite density than the.
I already work very hard, but I I agree.
It's more than that.
Yes.
It's much weaker as you would.
So what you can do is you can plot. You can numerically do a kind of fit for low frequency. We've determined the power, and the power sigma of omega at t equals 0 goes like some number, actually times omega to the power 3 minus 4m, and that's for m again between minus 1/2 and 1/2. If you go to the interesting point of m equals 1/2, well, then you see here 4 divided by 2, you get 3 minus 2 is 1. That would be the linear growth again. But for the m equals 1/2, we have to basically not forget that there is the logarithmic contribution. And for sigma equals 1/2, you actually get omega log omega, which is kind of mimicking the Coulomb interactions that the condensed matter people have found. So this is where the program is at the moment. We are also computing heat conductivity. It's not much harder than this, and here there's no condensed matter result yet, so we hope to be the first to produce some formulas for heat conductivities. And so I want to conclude here just in time saying that, well, these Weyl systems, they have kind of interesting physical stuff, and the message is that holography seems to be kind of able to describe these chiral systems in a very natural way, and including the interactions and the first signs of the output of the physics, I think is kind of like in good agreement with the intuition that condensed matter people have about the system. So it's 11:30, so I'll stop.
Before it started, questions, are there any questions? I think you were pretty clear.
No.
Yeah, I can only explain what I understand well, so it has to be clear.
I have the picture.
So it was crucial to split in the sources of this Weyl fermions.
Yes, that's crucial, but that, I wouldn't call this our kind of contribution. It follows from the general framework, and so we just had to borrow the result from MIT Leiden and just apply it to one dimension higher, and then you get the chiral fermions come out automatically, and so that's why that observation nobody kind of like made. It's a trivial observation, but it's kind of nice.
And on the condensed matter side, the question is just right, so you have a similar basic physical philosophy that you have these vegetable-free fermions that are not very interesting and they're popular with condensed matter systems, and they interact with some deep infrared, quote unquote, right, which is quantum critical, as we would call it.
Yes.
At the moment you.
Yeah. So this is mimicking this
kind of
relatively. Yes.
interesting quantum critical deep infrared, and okay, now if you see superconductor, you seem to have it, and if you start empirically.
Yeah.
In this business stuff, I fear it's a bit too colorful there.
I must say, I had a look at these experimental papers and the band structure. I ran away immediately. It is.
Yeah, it's just like so they are basically very conventional semiconductors. In a way, the electrons are more quiet than in silicon. Right, in the silicon you don't have interest in deep infrared. Right?
Yeah.
It's all free particles.
Interesting on abricosov looking for this bismuth time compound, but bismuth looking in the same framework.
I see.
So here would three-dimensional this Weyl fermion Hamiltonian from
So
just
because
very,
I
very
figured out
sophisticated arguments,
I
not
see,
from that
yeah.
structure, just from
There's another material based on cadmium arsenicum, but I know too little about it to say something sensible.
Yeah, so it's very interesting. All these things that are doing topological tricks are all extremely poisonous. And the reason is they need a lot of spin-orbit coupling, and for that you need to be an happy element. But apparently spin-orbit coupling is very unhealthy for people.
I see.
You also get a power law in T at omega equal to 0?
That's ongoing. Maybe by now Vivian has it, but we think it is basically the same power law.
So you get omega over T.
I think it's I think it's exactly. It's dimensional analysis. It's the scaling properties. Just says that at omega equals 0 for non-zero temperature, we expect the same scaling to as it should be. I think because all these functions are functions of omega over t too. Well, yeah, I hold it still. Yeah, it still has to be sure, but that's what we expect.
Numerically true.
Okay.
Okay, let's take stuff.